Hi guys, my name is Chris Jackson and I'll be going over my final tutorial on the thermal fatigue analysis of a brake rotor in racing applications. And this is really just going over CPO2, CPO3, and just carrying out the rest of the simulation. So here you guys can see an overview of the dimensions of the rotor, and this is within SolidWorks. The next video that you'll see is actually modeling the rotor in SolidWorks. So if you guys have any questions about any inputs that I used to create this rotor, you guys can refer back to this.
So here's the start of me modeling the rotor in SolidWorks, and you want to make sure that the units are in millimeters. This is what I use to draw everything in, and we're going to create our sketch off of the front plane. And this circle serves as the OD of the rotor, and this circle serves as the ID. And we're going to set that at 220 millimeters for the OD and 120, or excuse me, 140 as the ID. And once that sketch is complete, we're going to go ahead and we're going to extrude that from the front plane outward at 4.064 millimeters. And this serves as the body of the rotor itself that pretty much makes contact with the pads. And we're going to go ahead and now we're going to draw some of the tabs that the rotor actually uses to mount itself to the hub assembly. And our the OD of this circle is actually the ID of the body of the rotor itself, and then that secondary ID circle is actually going to serve so we can draw the profile of the tab out. So you can see here that the line is connected to these two intersecting points. And these are the outer profiles, and everything's in symmetry here. So we're going to go ahead and we're going to make this that 12.5 millimeters from this plane that you see here. And here I'm just making sure that, like I said before, same diameter of the ID of the body of the rotor itself, so that everything's as a whole. And this circle that you saw that I just drew within the sketch, this serves as where the bolt can actually slide through to mount to the hub. And actually, when I run my ANSI simulation, I'm going to use this as my fixed point. And once the sketch is complete, here I went ahead and I trimmed all the entities that I didn't need, and you'll see, that I'll have a closed sketch of the tab itself. Like just before, once the sketch is complete, we're going to go ahead and extrude it, and it's set at the same thickness as well as the body of the rotor. So now that that's complete, we can go ahead and we can include one of the other features that I like to use. It's a fillet, and it's going to go ahead and round off some of these edges that you see here. That's pretty sharp. And we're selecting 4 of the edges, and once those are selected, we're going to set those at 2.54 millimeters. So now that we have one tab that's complete, we can go ahead and we can select both the feature and the extrusion, and we can create our circular pattern off of this edge that you saw me click, and that's at 360 degrees, and we're going to create 6 of them. And here you'll see that we have our part that is actually, it's complete and it's ready to go. So moving on, within SolidWorks you can select different materials, and here's a materials property list that I came across. And I'm going to go ahead and import this into ANSYS as well for my simulation. And this is going to serve as my baseline. So you can see that we have different properties such as the elastic modulus, Poisson's ratio, tensile and yield strength, tangent modulus, thermal expansion coefficient, mass density, and hardening factor. And once I establish my baseline, I can go ahead and I can look at these different materials that could be a potential alternative as to what it can improve on the performance of the cart, and compare that under the same boundary conditions in the same analysis. So once I have everything selected as far as the material property and the geometry that's was just created, I want to go ahead and show you guys how I import it into ANSYS, and it's pretty straightforward. But here we're going to select our proper unit just like we did before, and we're going to set it as a steady state thermal system. And we can go ahead here and select right-click geometry and import your file. And you want to make sure that it's an IGS file, .igs, and that's to make sure that it can be properly imported into ANSYS. And once you double-click model, the actual part itself should populate and show here. And if it doesn't appear, there is a tab like a lightning bolt that says generate next to it. If you click that, it should show. And here you can see that the part is successfully imported.
So now that we've already modeled the part and everything, and we've imported it into ANSYS, I'm going to go over some of the boundary conditions and constants of this simulation. So the geometry of the rotor, the thermal characteristics, static structural characteristics, and step controls such as time, those all remain constant. They're not changing. And you can see here on the right, again, these are just overviews of the boundary conditions that have been applied. Static structure, we have fixed supports applied to each of the tabs. There's a force in the y and the negative y direction, and there's also a moment applied. Under steady state thermal, we have heat flux, convection, and radiation applied as well. So again, if you guys have to refer back to this for input values into what's going on into Workbench, go ahead and refer back to this one. And on the bottom left, you can see this is just an overview of the model tree within Workbench, that this is what it should look like.
And here you can see there's two different systems, like I mentioned earlier, a steady state thermal system and a static structural system. And the first three categories, engineering data, geometry, and model, they're all hand in hand. They're constant, so they have the same values and the same everything. They're set up the same. What differs here is in system A, it'll carry out its simulation and its analysis under thermal states, and it will pass it on to the static structural system, and the system will consider this in its analysis. And you'll see later the plots are actually within that system as well. And here's my initial material, and that's structural steel. And I'll go back here and change that once I choose a better fitting material. So this is the initial geometry that I imported in the first video, and this is my sketch that I just created, and this is where the pad meets the rotor, and that created three different bodies. Model, you can see that the same different sections of the body that was created, from that pad to rotor interface. Here are the contact regions. And here under steady state thermal system, you'll see that I have my constants that I refer to. Here's the mesh, but here is where I set my initial temperature as 22 degrees Celsius, my time setting at 3 seconds. And here under heat flux, the magnitude is 23,451 watts per meter squared. This was applied to where the pad meets the rotor, so that surface. And here it was applied to the whole face of the rotor, but not the lip that you can see here. And that's at a film coefficient of 230 watts per meter squared Celsius and ambient temperature 22 degrees Celsius. And here, it covers the same areas or the same faces, and it has that same ambient temperature of 22 degrees Celsius under radiation. So now that it's completely set up, I solved it and I got my first plot, and this is the thermal plot, and I have my max and my min. Max of 99.3 degrees Celsius and my min of 73.8 degrees Celsius. total heat flux. And again, it's my distribution here as well as a max and a min. Now considering this, we're going to move on to the static structural system. Same analysis system, but I applied fixed supports here, and there's 6 of them, and this is where the bolts would fit into the rotor itself. And here is the force applied from the pad to the rotor, both in the y and negative y direction, with a magnitude of 2,586 newtons. And I applied a moment as well, and you can see in that shaded area right here that that is the only surface that was selected, and that's at a magnitude of 179.76 newton meters. And here is the imported temperature from system A, like I'd mentioned previously. So now being completely set up, I generated my total deformation plot with our max and our min. And among the other plots, this is another good one that I can use as a comparison purpose when I select different materials. And here you can see my plot with the equivalent stress. So these are just still images that I use, and these are going to be the images, when I go ahead and I carry out, further analysis. I'm going to refer back to these. They're the same images as from, what you've previously seen in the video. But this is my temperature plot under the steady state thermal system. This is my total heat flux plot. This is total deformation, and this is under the static structural system. And this is equivalent stress.
So now that you guys have the initial setup of the baseline rotor with the static or the structural steel, we can go ahead in there and we can change some of the material properties and really see what that has an effect of the life of the rotor in reducing damage due to these cyclical stresses and strains and heat that the rotor experiences through heating and cooling. And this is what that next video is. So we saw previous plots, but here's plots of damage as well as life of the stock rotor, and this is pretty much what I wanted to focus on in this project. Really seeing the effects of life due to these different conditions that we apply through racing scenarios. And again, you can see different parts of the rotor. These are all applied as structural steel. We're going to go back and change material properties. And here you can see the different elements that you can include or different materials: aluminum, hardened steel, structural steel. And here are the different properties that you can use. And actually, under hardened steel, I went into alternating stress, mean stress, and I included alternating stress and cycles. And this is all based off of data that I got from Boeing to further customize my solution based off like specific materials that I wanted to use. So we're going to go back here and we're going to change some of the bodies, the materials of the bodies. And I chose to change this inner lip just because if you look back at the stresses and the actual life of the rotor, this is the main area that is affected. So I figured let's try to harden this and see what kind of effect it has on the rotor. And once we update that, we're going to go ahead and look at those same plots of the damage and the life of the rotor after we've changed this material. So here we can see that we have our solution, and then we're going to look at the damage plot, or actually the temperature plot first, and these are just the same plots that we saw before. Here's total deformation, equivalent stress, and I went ahead and included equivalent elastic strain as well to this as a new part of the solution. And here again, this is the damage, the actual damage of the rotor, and it's significantly improved over what our baseline results were. And the same thing with life. And you can see life of that inner lip is greatly extended just by changing it to a hardened steel, as well as reduction in damage. So now having that result, for comparative purposes, we're going to go ahead and explore different configurations as well. And I went ahead here and applied the rest of the bodies, so bodies 1 and 3 as hardened steel, and I went ahead and looked to see what that did to the rotor. And if you guys want to explore any other materials, all you have to do is go ahead back to engineering data, add that to your list, and then go back to the geometry under where the bodies are created, and change that assignment to whatever material you'd like and have a different solution. So here are the results of the completely hardened rotor, and obviously this is the optimal solution in comparison to just the inner hardened lip. When we're looking at damage here, you see like a completely non-existent distribution, and this is just because it's every factor, like the factor of safety, everything is satisfied here. It's optimal. It's extremely high. That's why it's the same. Um, but something like the previous solution, we could see more of a distribution in the damages, because that's something to really consider. And here I change it to everything to aluminum, so I change everything to aluminum. And by nature, I know it's a softer material, but I wanted to use this to compare it again, just to see what it really does to the effect of the rotor, the performance of the rotor, and how strain or deformation or the life of the rotor is really affected by this. And again, here you can see temperature plots with min and max, total heat flux, deformation, equivalent stress, elastic strain, and this is actually doubled compared to what our previous solutions were. And here's damage, and here's life of the rotor. So you can see it's not really the optimal solution. I went ahead for the sake of this project and selected the rotor that has the hardened inner lip as the optimal solution, just because that's what it experienced the most damage and the most reduction in life of cycles. So it didn't really make sense to harden the complete rotor in a business sense, but that would be the ultimate design in comparison to the materials that I considered here. So I want to thank you guys for your time. These are the sources that I used. If you guys have any questions, please feel free to reach out. Additionally, there's another PowerPoint presentation that I included that includes all of my results. So if you guys want to consult that as well, go ahead and feel free to do so. Thank you guys.